We are discussing the IIT-JAM 2011 modern physics question. Again, I am reiterating it. In 2011, there are two kind of question, MCQ each of 6 marks and subjective problem 21 marks. So this problem is for 6 marks. Let us read the statement of this problem. Light described by the equation E, 90 volt per meter, sine 6.28 tan ki power minus 10 to the power 15 per secant and sine 12.56 into 10 to the power 15 per second is incident on a metal surface. The work function of metal is 2 electron volt. Maximum kinetic energy of the photoelectron will be. So we are having it. Solution. We have E is equals to 90 volt per meter sine 6.28 into 10 to the power 15 second inverse into t plus sine 12.56 into 10 to the power 15 second inverse t. We can write it down as where omega 1 is equals to 6.28 into 10 to the power 15 second inverse and omega 2 is equals to 12.56 into 10 to the power 15 second inverse. Work function W naught is equals to 2 electron volt and E naught is equals to 90 volt per meter. Now, the maximum kinetic energy is given by Ke max is equals to E minus W naught. ठीक है. So for frequency omega 1 equals to 6.28 10 to the power 15 second inverse. Kinetic energy is Ke max is equals to 6.6 into 10 to the power minus 34 into 6.28 into 10 to the power 15 divided by 1.6 into 10 to the power minus 19 minus 2 equals to 2.125 electron volt. Similarly, kinetic energy maximum for divided by that was omega naught. So we have to divide it here 2 to 3.14. I missed it out. So that was the correct kinetic energy maximum for angular frequency omega 2 is equals to 12.56 into 10 to the power 15 per second is Ke max, that is 1 max 2 6.6 into 10 to the power minus 34 into 12.56 into 10 to the power 15 divided by 1.6 into 10 to the power minus 19 into 2 into 3.14 minus 2 equals to 6.28 electron volt. Thus, the maximum kinetic energy would correspond to frequency 12, angular frequency 12.56 and its value would be 6.28. We should not have calculated with this frequency, angular frequency, as it is half, so maximum would be given with respect to maximum incident energy. The wave function of a quantum mechanical particle is given, where phi1 and phi2x are eigenfunction corresponding to energy eigenvalue minus 1 electron volt or 2 electron volt respectively. The energy of the particle in state psi is, So we have solution. We have capital psi of x is equals to 3 by 5 phi 1x plus 4 by 5 phi 2x. Now we have this. Further, psi of psi is equals to 1. As we can see it, or writing psi of psi is equals to 9 by 25 plus 25 phi 1 of x into phi 1 x plus 16 by 25 phi 2 of x into phi 2 of x equals to 9 by 25 plus 16 by 25, that is equals to 1. So psi is normalized. The average energy of the particle is given by, that is average A is equals to summation Pi Ei, which is equals to probability of the finding the particle. We can write it here, left here. Probability of finding the particle in state phi 1 is that is P of phi 1 is equals to phi 1 psi mod square, that is equals to 9 by 25. And similarly for state 2 phi 2 is with energy E1 is equals to minus 1 electron volt and E2 is equals to minus 2 electron volt. So we can write it down minus 9 by 25 into minus 1 volt plus 16 by 25 into minus 2 electron volt, which is equals to 32 plus 9 minus 41 by 25 electron volt. Let us check which answer is correct. Option A is correct for this problem. Let us discuss this subjective problem of 21 marks. Here, a particle of mass m in a Vx potential is given by, where potential is defined, that is the region 1 and this is region 2. Write down the general solutions for wave function in region n first if the energy of the particle is E0 and V0. Using appropriate bounding condition, determine the equation relates to E to V0, M and L. Now set V0 equals to 0 and assume that a beam of particle is incident on infinite step with a potential x greater than potential from x greater than 0 and E0. Using the general solution for this wave, using the general solution for the wave function, calculate the reflection coefficient. So we have to determine the reflection coefficient for the solution. We have V of x is defined as 0 in the region x less than m and V0 for x greater than m. Now Schrödinger equation in region first First is given by, that is h psi equals to a psi implies minus h square by twice m del square psi by del x square plus equals to e psi implies del square psi by del x square plus 2me by h cross square psi equals to 0 or del square psi by del x square plus alpha square psi is equals to 0, where alpha square is defined as 2me by h cross square. Now thus we can take it equation 1. The solution of equation 1 is given by psi x is equals to a sine alpha x plus b cos alpha x. Now applying boundary condition, I would be writing psi first here. First boundary condition, psi first x equals to 0 would give us 0 implies b is equals to 0. So our solution psi first of x would be a sine alpha x. Similarly, Schrödinger equation in region second is given by, that is h psi second equals to e psi second equals to implies minus h square by twice m del square psi second by del x square plus v of psi second equals to e of psi second implies del square psi second by del x square minus twice m by h cross square v minus e of psi second equals to 0. Now we can write this equation like del square psi second by del x square minus beta psi second beta square equals to 0, where beta square is defined as twice m by h cross square v minus e. So we can write it v naught here. So we would be the solution in region second from above equation is given by that is psi second equals to x e to the power c equal to the power minus beta x plus d e to the power beta x. Applying limiting case, that is limit x tends to infinity psi second x must be 0 implies limit x tends to infinity c e की power minus beta x plus d e की power beta x must be equals to 0 implies d is equals to 0. Thus, psi secant x is nothing but c e की power minus beta x. Now, applying boundary condition. At x is equals to L, we have psi 1 at x is equals to L must be equals to psi secant at x is equals to L del psi first, but del x at x is equals to L must be equals to del psi secant by del x at x is equals to L. This gives us a sin alpha L is equals to c e to the power minus beta L. This gives a alpha cos alpha L is equals to d minus d e to the power, that is c minus c beta e to the power minus beta L. Now this equation we can take it 1, I can take it 2, this equation can be taken 3, divided on dividing, we can divide it here rather than, so we get it tan alpha L divided by alpha is equals to minus 1 by beta, or I can write it down 1 by alpha cot alpha L is equals to 1 by beta with negative alpha cot alpha L is equals to minus beta. We can multiply it with the equation L, so we would be having it like alpha. Now taking alpha L is equals to J and beta L is equals to eta, we would be having it as hypothetic equation J cot equals to minus eta. Now if we add alpha L plus square of J square plus eta square, we would be having it here J square plus beta square, J square plus eta square is equals to alpha square plus beta square into L square, which is equals to twice m v naught by h cross square into L square, and this can be taken as r square radius. So plotting this equation, I would be taking 4, this is 5, plotting the curve for cot eta versus J with respect to cot J. This is the equation as for the question which relate energy with the potential and length and mass. Now one can solve this equation as we know it from pi by 2 to pi, 3 pi by 2, 2 pi. Between 3 pi by 2 to 2 pi, cot curve increases. Since the question does not require the solution, so we are not going to make it our plot for the problem. Let us move on to our part B. Now, in the part B, question is saying assume V0 is equals to 0, means particle is coming from here and striking the infinite potential and going back. So for this, we have to determine using the general solution is incident on infinite step potential from x greater than 0 with energy greater than. Using the general solution for the wave, calculate the reflection coefficient. So we have to determine what could be the reflection coefficient for this. General solution for the wave function. Now, solution for B. In this region, if the particle is coming from here and striking this infinite potential, so this particle would be reflected back, and even this particle would be reflected back from the infinite. There is no probability that it would move. There is no possibility that this particle tunnel through the infinite potential. Okay? Now, so theoretically, the value of reflection coefficient for this potential would be 1. Now let us write it down. The Schrödinger equation. The Schrödinger equation in the region x, there are two regions, x greater than 0 and x less than 0. So in the region x greater than 0, we have h psi is equals to E psi implies minus h square by twice m del square psi by del x square is equals to E psi implies del square psi by del x square equals to 2me by h cross square into psi is equals to 0. So again we can take it this alpha square is equals to 2me by h cross square. For scattering, the solution of del square by del x square plus alpha square psi would be 0. This implies solution of psi first in the region would be a e to the power minus I alpha x plus beta e to the power I alpha x. Here this term represent incident wave and this one represent reflected. Further, so if in Schrödinger equation in region x less than 0, we have h psi equals to 0 into E psi. Since potential is 0, so there would not be any equation here, because potential beyond this region, in the region second is infinity, we cannot write it down minus h square by twice m del square psi by del x square plus v. Here v is approaching infinity, so we cannot write it down the Schrödinger equation here like this one. That's since particle cannot penetrate infinite barrier, that means psi in the region x less than 0 is equals to 0, which if psi is in this region is 0, then J trans would be 0. That means reflection transmission coefficient, which is defined as J trans divided by J incident, is equals to 0, which means R is equals to 1 using property R plus T equals to 1. Further, J R can be defined by J reflected by J incident. Here for psi incident, as I said, it is e to the power minus C A e to the power minus I alpha x, which give us J incident would be defined like this: h cross by twice mi into minus psi star del psi minus of, here you would be having it, psi grads psi star. So what I would get, J incident would be h cross by twice mi. Here I would be having what, e to the power I alpha x minus I alpha e to the power minus I alpha x minus I alpha x minus I alpha e to the power minus I alpha x. Not this term is not minus but positive. So I would be having minus of h cross by m alpha, or mod a square is common here and here, into mod a square. Now similarly, J reflected will be h cross by twice mi psi mod star psi minus psi mod psi star. For J reflected, and psi reflected here would be equals to B e to the power I alpha x. Now once I substitute, we get h cross by twice mi. I have taken mod b square outside, so here you would be having it I alpha minus of minus I alpha equals to h cross m alpha mod b square. So for the reflection coefficient would be J reflected by J incident, which is equals to h cross alpha mod b square by m divided by h cross alpha by m into mod a square, which is equals to mod b square by a square, and that is equals to 1. So this is how we can check it out, and both these coefficient implies mod b is equals to mod a. So these are the solution of 21 marks problem.